We're going to talk about how graphs and derivatives and integrals are all interconnected and interrelated. So first of all, this first question says, if the graph of a function is always concave up, like we have here, then the left-hand Riemann sum. So let's make a left-hand Riemann sum. What that means is that wherever you start with your x, you come up to the function and the left side of your rectangle quits at the function. So if I come up here and I quit the left side of my rectangle at the function, and then let's come up here and quit the left side of my rectangle at the function, you can see that it's always going to be an underestimate. Now, if I do the same thing with a right-hand integral, if I start here and I wait till the right side of my function, see that? It's the right side of my rectangle is touching the graph. Now you're going to see, let's let this one, let's draw one here that's a right side. I go up, but I got to go up until the right side touches the graph. And let's do another one here. I have to go up until the right side of my function, of my rectangle touches the graph. And these are all overestimates. Notice they all go above the graph. So the answer to the question, if the graph of a function, okay, so if the graph is always concave up, then the left-hand Riemann sum with the same subdivisions, which we did here, over the same interval, are always less than the right-hand sums. And we know that's true because this left-hand one underestimated it, whereas the right-hand overestimated it. So this is true. Now, this one was a little bit trickier, so I want to do it last. So I want to answer question number 3 here first. So here's the way that derivatives work. If f of x is increasing, then the first derivative, f prime of x, is positive. Okay, now, if f prime is positive, okay, I don't want to say it that way. If f of x is concave up, that means that the second derivative is positive. Okay, positive. And then you can do the same thing with decreasing, just for the fun of it. We'll put those here. If f of x, the original function, is decreasing, then f prime of x is negative. You can say that is f prime, the original function f of x is concave down. That means that the second derivative is negative. And you can also say that if f of x is neither increasing nor decreasing, like at a minimum or a maximum, like at a relative minimum or maximum, then the first derivative is 0. And if f of x is neither concave up nor concave down, then the second derivative is 0. We call these inflection points if the concavity changes. So, looking at question 3, what question 3 is saying is this. Question 3 says, let me do this. Okay, here's what question 3 is saying. It says, if f prime of x is greater than 0, they are saying that f, try again. They are saying that f prime of x, when they say it's greater than 0, they're saying it is positive. Okay, it's above 0, which tells us that the original function, f of x, is increasing. It says nothing about the concavity, because I can draw you a function that is increasing. Let's make it green and thick. Here's what it means for the original function to be increasing. Okay, I can have an increasing function that is concave up. It would look like this. But I can also have an increasing function that is concave down. And I will draw it in orange, and it would look like this. Do you see that that's increasing but concave down? The orange one, the pink one, is increasing but concave up. So the derivative doesn't tell you anything about concavity. The second derivative tells you about concave up or concave down. The first derivative only tells you whether the original function, f of x, is increasing or decreasing. So this one is false for sure. Okay, now we need to talk about number 2. This isn't exactly Rawls' theorem, and it's not the intermediate value theorem. It is something else. And I want to explain it with pictures because words alone just aren't going to cut it. Okay, so let's start question. Let me write question number 2 here. This is going to be start over. This is going to be question number 2. So, function f is continuous on the interval a to b. So, and a doesn't equal b, so let's make, and the interval starts at a and ends at b, so a is less than b, so let's make this a to b. Let go. And I think, okay, well, let's just do it this way. Now, here's what it says. So f of x is continuous on this interval. It includes these points. A doesn't equal b, And what they're saying is that the integral from a to b of f of x equals 0. Okay, they're saying this is true. Oh, I need a dx in here. Let's make it official. F of x dx equals 0. Okay, probably I should say equals. Okay, this is what the problem tells us. We have an integral from a to b. It's going to be continuous and include the endpoints. Here, a does not equal b. And the integral from a to b of f of x dx equals 0. They're saying then the original function must have at least one 0 between a and b. Okay, so I can draw all kinds of functions in here. I can have a straight line. I can have something that bumps up and down. I can have something that goes straight down. So how do we know, how do we make this be true? Well, the thing about integrals is that they represent the area under the curve. Okay, this is the area but I don't like that word because sometimes it's above. This is the area between the curve and the x-axis. That is the physical representation of an integral, is that it is the area between the curve, which is our f of x, and the x-axis. That's what integration represents. So the only way you can get the area between f of x and the x-axis is if you have the same amount of area between the x-axis and f of x above the axis as below. So you could draw something like this, and as long as this area below is the same as this area above, this integral will equal 0. Because this integral represents the area between this function right here. This is the function. Maybe I can make it bold. Here's the function. And so this would be your at least 1, 0 right here where it crosses the x-axis. Now, if I would move this up, this integral wouldn't equal 0 because all the area between my curve and the x-axis is positive. And if I move it down, this area now, all the area between this curve and the x-axis between a and b, it's all negative. So the only way to get that integral to equal 0 is if the area from the curve to the x-axis above is the same as the area from the curve to the x-axis below, because this is positive area and then this is negative area, and if they have the same area, they cancel each other and become 0. You could do this with a line if you wanted to. The only way I'm going to get, what if I just make a line? Well, notice that the area under this curve now is a right triangle, and it's negative. Oh, I'm going to have to turn it around. I can't use this. Can't use it. Never mind. Anyway, this area, I'll make it red because it's, well, I want to just draw. Thank you. This area here is the same amount of area, but it's negative as this area here, which is the same area if I'd drawn it perfectly. And it's positive, and this plus this will equal 0. So even though this isn't exactly Rawls' theorem, and it's not really the intermediate value theorem, this answer is true. Because the only way to get that integral to equal 0 is to have the same amount of area above the x-axis as you have below the x-axis, which means you had to pass through 0. Thank you.